Section 8.2, inverse trigonometric functions. Our objectives are to define the domain and range of the inverse and to use inverse trigonometric function notation. Inverse trig functions is just another way to solve trig equations. We learned in 8.1 how to solve trig equations graphically. Now we're going to solve them using inverse trig. A review of inverse functions. So in order to have an inverse that is a function, we need to have our original equation of f be a function. And if that's true, then the following statements are equivalent. So the inverse of f is a function. F would then have to be a one-to-one, or we say one-to-one correspondence. And remember, for something to have a one-to-one correspondence, that means that the graph of f would have to pass the horizontal line test, which I always abbreviate HLT. And also, of course, remember that inverses and functions are reflections across the line y equals x. So if the inverse, if it exists, is written as f inverse, remember that that does not mean f to the negative 1 power, it means f inverse, where if y equals f of x, then x is equal to f inverse of y. So for this first function that we're going to look at the sine function. Now for this sine function, just to recall, remember that our domain is from negative infinity to infinity, and our range values are from bracket negative 1 to 1. Now for this, I know that the sine function does not pass the horizontal line test. And just to show you, here's a horizontal line, and if you look, it goes through a lot of different places. So because of this, I know it doesn't have a one-to-one correspondence, so it doesn't have an inverse that is a function unless I restrict the domain. So the question is, where do I restrict these domain values to in order to get an inverse that is a function? So let's start at 0, 0. So if I start at 0, 0 and take my graph and start to go this way, and as I get to here, if I keep on going, I would not use this as my restriction. Why? Because if you notice, if I use that part as my restriction, then it does not pass the horizontal line test. So I need to go back and erase my graph up to where we stopped at pi over 2. Well then, can I go backwards and still be a function? So I can go backwards to here and my graph is still a function. If I try to keep on going, notice then my graph right around that side would then not pass the horizontal line test. So the only time it would pass the horizontal line test is if my values are in between negative pi over 2 and pi over 2. So I would take a highlighter and I would highlight this part of your graph. Because if you notice that we do that, now that makes my graph pass the horizontal line test, so it would have a one-to-one correspondence and my inverse would be a function. So that means we're going to purposely restrict our sine graph domain on the interval from negative pi over 2 to pi over 2. So we're restricting it from here to here. So now that I have my restrictions, I can go ahead and graph my inverse equation. So for this, my inverse, I switch my x and my y. So my inverse would be x is equal to the sine inverse of y. So that means I'm going to take these x and y coordinates and switch them and graph them over here. So for my inverse, I have, or for my graph of sine, I have the point pi over 2 and negative 1. So over here, I'm going to have the point negative 1 pi, negative pi over 2, because I'm switching them. So that would be right here. And if I do the point 0, 0 and switch it, it stays 0, 0. And then if I do this point up here, I have pi over 2, 1, which is going to become 1 comma pi over 2. So notice that we switched our, again, domain and range values. Now, I guess I should have drawn that better. So for the inverse, remember it's a flexion of the line y equals x. So if this part right here curves downwards and then curves upwards, I know that this is going to kind of curve the opposite way, so it looks something like that. So this is going to be the graph of my inverse. Now if you look at the domain here, remember we're switching our domain and our range from our original sine function. So if my range was originally negative 1 to 1, that becomes my domain. And then my range values, remember we restricted our domain values from negative pi over 2 to pi over 2. So that means that my range values are going to be answers from negative pi over 2 to pi over 2. And if you think about this on your unit circle and you think about your answers, if you have negative pi over 2, which would be down here, and this is pi over 2, notice that we're in quadrant 1 and quadrant 4 on my unit circle. So those for the sine inverse are going to be the quadrants that I'm working with. So I'm going to work with quadrant 1 and quadrant 4 for my answers. So you have to be very careful when you are writing these answers out, because you can only have answers that are in quadrant 1 and quadrant 4 from negative pi over 2 to pi over 2, because we are purposely restricting our domain values. Now, a couple of different ways that we can write the inverse. So we can write it using this right here, so sine inverse of x, or a lot of the times you'll see in books that it's written as the arc sine of x, which means the angle or arc whose sine is x. The reason that books usually write arc sine of x is because a lot of students get confused with the -1 and they think that it's not an inverse, they think of it as an exponent. So you'll see a lot of people write arc sine just so that people are not confusing it with an exponent. So a couple properties of sine that we have for the inverse. So notice that for these properties, there's two different ones. This first one, if you have the sine inverse of the sine of x, it is equal to x if and only if negative pi over 2 is in between, or x is in between negative pi over 2 and pi over 2. And the second property is if you're going to do the sine of the sine inverse of y, only for values of y that are in between -1 and 1. So let's do some examples to think about this. So remember up here on the sine graph, when we're evaluating this on my unit circle or on my graph, I'm taking the sine of an angle and I'm getting answers that are in between -1 and 1. Well, if I'm doing the inverse where I'm switching that, then I'm given things that are on my unit circle and I am trying to figure out, well, what angle would that be then by using my inverse? So for these properties, just to look at this first one, if I'm doing the sine of x and I have an inverse in my equation as I do right here, well, that means that if this inverse is my equation, I can only have values of for my angles that are in between negative pi over 2 and pi over 2. Otherwise, I cannot evaluate the inverse of the function. And that's because we have to restrict it to do inverse equations. So if I look at this first one, I have the sine inverse of the sine of pi over 4. So in order to evaluate this, well, what's the sine of pi over 4? So think about your unit circle. You're in quadrant 1. The sine of pi over 4 would be equal to root 2 over 2. So I'm really, for this equation, doing the sine inverse for root 2 over 2, and I'm trying to figure out, well, what angle gives me the sine inverse of root 2 over 2? So now we're going backwards from what we just did. So if I go backwards from what I just did, I'm saying the sine of what angle on my unit circle gives me root 2 over 2, and because I'm working with sine inverse in my equation, I can only have answers that are in between negative pi over 2 and pi over 2 because we purposely restricted our graph to do that. So for this, I know that I can only work with quadrants 1 and quadrants 4. So in this case, since the sine is positive root 2 over 2, I know that my answer is going to be equal to pi over 4. Now if we look at the next one, we have the sine of the sine inverse of 1/2, and it says that these values have to be in between -1 and 1. The reason that is because I don't have values on my unit circle that are above 1 or a range value that is below -1. So I can't find an angle for something that's above 1 or below -1 for the sine. And so because of that, I have only values that can be in between -1 and 1 because of my unit circle. So if I have the sine inverse of 1/2, I have to think about what quadrant I'm in. So for inverse in my equation, I know that I can only be in quadrants 1 or quadrants 4. So these are the only half of the unit circle that I'm using. If the sine is a positive 1/2 value, then I know I'm going to be in quadrant 1. So this tells me again, quadrant 1, because it's positive 1/2. If it was negative 1/2, then I would be in quadrant 4. We don't even work with the other side of the unit circle for these inverse equations. So the sine of 1/2 I know is equal to pi over 6. So I'm really doing the sine of, in this case, pi over 6. And then I would say, okay, well, what's the sine of pi over 6 on my unit circle? It's equal to 1/2. So remember that when you're doing inverses, you are switching your x and your y values. So if you do the sine inverse of the sine, you're basically undoing what you just did, and vice versa for the one that we just did in blue. So that's why we get pi over 4 or 1/2 out. But you have to remember it's restricted to these values for each of the different equations. So for example 1, let's evaluate some of the following. So if I want to find the sine inverse of root 3 over 2, because I have an inverse in my equation, I know I can only work with quadrants 1 and quadrants 4 on my unit circle. So again, I only have this side to work with. I'm not even doing stuff on the other side. So for this, if I write this without the inverse, basically what we're trying to do, if I set this equal to x, we're saying the sine of what angle is equal to root 3 over 2 on my unit circle, but it has to be either in quadrant 1 or quadrant 4 because we had to restrict our values when we're working with the sine inverse. So for this, root 3 over 2 I know is going to be in the first quadrant because it is positive. So if I want to find the sine of root 3 over 2, I have to think about, well, what angle gives me root 3 over 2 on my unit circle? So if I think about that, I know that it's going to be pi over 3. So this equation right here, I'm going to erase this, is really equal to pi over 3. Oops. Because the sine of pi over 3 is equal to root 3 over 2. And again, my answers are always going to be in quadrant 1 or quadrant 4 when I have an inverse in my equation. So the next one for B says the sine inverse of negative 1/2. So the sine inverse for negative 1/2, now if I think about this, this is a sine of a negative angle. Well, where is the sine negative on my unit circle? My negative sine values are down here in quadrant 4. So I have to say to myself the sine of what angle is going to be equal to negative 1/2 on my unit circle in quadrant 4. And remember, we're restricting our values from pi over 2 to negative pi over 2. So I can't use the angles that are normally in my unit circle, the positive angles. I have to use negative angles in this case because we're in quadrant 4. So the sine of x is equal to negative 1/2 when we have this value right here, which would end up being negative pi over 6. And again, I can't use 11 pi over 6 because 11 pi over 6 is not in my restricted domain. So this is equal to negative pi over 6. And if I keep on going for the next part, now instead of writing the sine inverse in my equation, we have arc sine. So if you want, this is the same thing as saying the sine inverse of negative 1. So I have to figure out where is the sine equal to negative 1. So I know it's not going to be in the top half. It has to be somewhere in the bottom half. Well, I need a y value of negative 1. Where do I get a y value of negative 1? That would be all the way down here on my unit circle. So at negative pi over 2. So this is equal to negative pi over 2. Now I have this sine inverse of 2, or I could say the arc sine of 2. Well, remember we said before, if I try to rewrite this, the sine of what angle is going to give me 2 on my unit circle? Remember, your unit circle is a radius of 1, so your values are always going to be in between negative 1 and 1. So this is not even something that I can solve because it's not in my domain. So this would be no solutions. And again, it's because it's not in your domain, which we said before was bracket negative 1 to 1. So anything above negative or above 1 and below negative 1 would have no solutions. Now, if you look at E, this equation is different than the ones that we just previously done. For this equation, you'll notice that we don't have an inverse in my equation. If you do not have an inverse in your equation, then you don't have to worry about the restrictions for sine. So in order to solve this, I can just use my calculator and do the sine inverse of negative 0.67, and see what it's going to be equal to. So if I take my calculator, I would make sure I'm in radian modes when we're doing these. So if I do the sine inverse of negative 0.67, I get my answer equal to negative 0.7342. But remember before, when we were solving these equations, we said that, well, we want to find all the places where the sine of x is equal to that, because remember, our sine graph keeps going on and on forever, so we have many places that we're going to hit negative 0.67. So one place is negative 0.734 plus the period of my graph, which in this case would be the 2 pi n, where n is an integer. And if I want to find the other values, I could use my graphing calculator. So what I would do is plug this into my y equals. So we learned this in section 8.1. I set my equation equal to 0 by adding the 0.67 to the other side. And then on my window, I graphed it from 0 to 2 pi because that's the period of my function. And if I hit graph, notice that I see in this case, I see two places where I'm hitting on my graph. So in order to find those two places, I need to do second trace, and I need to do the 0. And so when I do left bound enter, right bound enter, oopsies. So when I do the first one, I get an x value of 0.3875, and then I'm going to do the second one. So I'm not ready. And then I would find the other value by doing the same thing. So when I do all that, I get these two answers right here, which we learned how to get. And so if I do the sine inverse, because it wasn't in my equation, I'm missing answers, because in this case, we were trying to solve the sine of x equals negative 0.67, where every other one we were trying to find the inverse in my equation. And so in section 8.3, we're going to learn how to find the second solution. And even if you notice negative 0.7342, if I add 2 pi to that, because the next answer that's going to be equal, the same distance from that would be adding 2 pi n, so 2 pi times 1, that would give you x equals 5.5489, which is the second answer on our graph. So there is a way to find these without having to graph them in your calculator, which we will talk about. But for right now, you can use your graphing calculator to show you that one. So even if you try to do some things on your graphing calculator, if I go to my home screen and I try to do, let's say, the sine inverse of 3 like we had before, I know this is going to be no solution. That's why it says error domain, because it doesn't fit within my domain. And notice that if I go to my y equals and I graph the sine inverse of x and hit graph, and I guess I should change my window, zoom 7. Notice that it only graphs what we had graphed previously from negative pi over 2 to pi over 2. So your graphing calculator does the same restrictions that we do. So now the next example that we're looking at is going to be this example right here. It says, explain why the sine inverse of the sine of pi over 4 is equal to pi over 4 is true, but the sine inverse of sine 7 pi over 4 equals 7 pi over 4 is not true. So let's look at what the not true one. So for this, I have the sine inverse for the sine of 7 pi over 4. So first of all, I want to figure out where 7 pi over 4 is on my unit circle. And when I figure out where 7 pi over 4 is, that's going to help me figure out what my solution is going to be. So 7 pi over 4, I know is going to be in the fourth quadrant down here. And for this, I know that the sine is negative in this quadrant, so the sine of 7 pi over 4 is going to be negative root 2 over 2. So if I want to do the sine inverse of negative root 2 over 2, I know it's in quadrant 4, but remember we said anytime I have an inverse in my equation, I have to restrict my values from negative pi over 2 to pi over 2. I cannot have answers that are above or below those two values. So I can't use 7 pi over 4 if I do the sine inverse of negative root 2 over 2. That would not be true because it's not on my it's not in my range values that I have. So because of that, I have to switch it. If instead I were to say, in this case, negative pi over 4, I know that that would be a true statement. So I could do the sine of negative inverse, sine inverse, sorry, of the sine of negative pi over 4 would be equal to pi over 4. But for this one, it was not true because 7 pi over 4 is not within my restricted inverse range values that we have, which again are from negative pi over 2 to pi over 2. So you have to be very careful when you're doing those problems. This one does fit within my constraint, so we're okay. So let's go ahead and go to the next part. So the next one we're going to talk about is our cosine function. So for our cosine function, if we look at this graph, we have the same problem that we had for the sine graph. I know that this function is not a one-to-one, does not have a one-to-one correspondence because it doesn't pass the horizontal line test. It fails in many different places. So because of that, if I want to find the inverse function, I have to restrict my domain values for my cosine of x. Now, where would be good values to restrict to? If I start at 0 and go this way, from 0 to pi would be a good place because it passes the horizontal line test. If I try to go any further than pi, we would not pass the horizontal line test. And if I try to go below 0, I would also not pass the horizontal line test. So this part in red right here, which I would highlight on your graph, it's going to be the part where we're restricting our graph. So our domain for cosine is still negative infinity to infinity, and our range for this would be bracket negative 1 to 1. But in order to do the inverse, we're restricting our domain values from 0 to pi. So for my inverse then, again, you switch your x and your y values. So this would be the cosine inverse of y is equal to x. So if I wanted to draw this, if I have the point 0, 1 on my graph, then I'm going to have the point 1, 0 here. If I have the point pi over 2, 0, I have the point 0 pi over 2. And if I have the point pi negative 1, I have the point negative 1 pi. So my graph is going to look something like this. And even if you were to go to your graphing calculator, you could confirm if I do, instead of sine inverse, cosine inverse and hit graph, notice that's what my graph looks like. So this is my inverse function. And so this is the inverse. So the domain, remember, comes from my range of my cosine graph. So the domain would be from negative 1 to 1. And my range values are going to be from my restricted graph because we want it to be a function. So my range is going to be from 0 to pi. So that means whenever I have an inverse in my equation, I have to restrict the values from 0 to pi. I cannot use any other values on my unit circle. So we call this the inverse cosine or the arc cosine. And just like sine, we say that because sometimes students get confused with the think that negative 1, instead of being cosine inverse, they think of it as an exponent, which is not true. So that's why you'll sometimes see people write it as the arc cosine. So we have properties for the arc cosine as well, which kind of are like the sine properties. So the cosine inverse of the cosine of x, this is a true property right here, only if your values of x are in between 0 and pi. And this statement is true only if your values of y are in between negative 1 and 1. So it's similar to the sine one that we just did. So let's evaluate the following. We want to do the cosine inverse of 1. So notice for all of these a, b, c, and d, we're doing the cosine inverse in them. So that means on my unit circle, I'm using values from 0 to pi. So I know it's going to be quadrants, in this case, 1 and quadrants 2. So I should write that up here. So quadrants 1 and 2 for your answers. So then down here, I have to think about from quadrants 1 to 2, where is the cosine equal to a value of 1? So the cosine of what angle equals 1 on my unit circle? Well, for this answer, I know that we get 1, an x value right here at 0. And it has to be answers in between 0 and pi, so the only answer I can have is 0. If we do the cosine, arc cosine of root 2 over 2, that means we're doing the cosine inverse of root 2 over 2. So we're saying the cosine of what angle on my unit circle will give me a value of root 2 over 2. Well, first I would have to think to myself, root 2 over 2 is positive, so would that be quadrant 1 or quadrant 2? Well, I know cosine is negative in quadrant 2, so it has to be quadrant 1. So where do we get root 2 over 2? Right here. So that would be an angle of pi over 4. And again, notice that we don't have multiple answers for these. We only have one solutions because we're evaluating the problem. We're not solving for x and finding all the solutions. So for the next one, the cosine inverse is equal to 1/2. So on my unit circle, again, I'm in quadrant 1. Where do I get the cosine equal to 1/2? It would be at the very top, right here, which is equal to pi over 3. If instead I had the cosine inverse of negative 1/2, then I would be over here on my unit circle, and so my answer would be equal to 2 pi over 3. And again, remember, because we have to restrict these inverse answers, I don't have any more than this, like we talked about earlier, when you have multiple answers for your when you take the angle of something, it doesn't work backwards for inverses. So for D, because it's not something on my unit circle, I'm just going to go ahead and use my calculator in order to find that. So on my calculator, I'm going to do the cosine inverse of 0.14, and I get this value right here. So that's going to be my solution. And I only can have one answer from 0 to pi, so I don't have to write anything else. So that would be my angle, because when you're doing the inverse, you're actually finding the angle. So the last one we want to look at is the tangent function. So for the tangent function, here's my graph, and for this function, if we look at this, again, this does not pass the horizontal line test, which means that the tangent is not does not have a one-to-one correspondence. So we want to restrict the domain value so that it does have a one-to-one correspondence. So if I do this first part of my graph right here, that would pass the horizontal line test and make my inverse a function. So my domain for tangent, remember, if you recall, is going to be all real numbers except for values cannot be equal to pi over 2 plus pi n. And the range in this case was from negative infinity to infinity. Well, now we're restricting our domain values to negative pi over 2 or pi over 2, but, well, look here and here. Because we have those asymptotes there, because it's undefined, tangent values are undefined at negative pi over 2 and pi over 2, we cannot put brackets. We're using parentheses because it's not equal to those values. So when I do my inverse, again, you switch your domain and your range. So your domain becomes negative infinity to infinity for tangent. And my range are going to be values from negative pi over 2 to pi over 2, not including. So again, we know that the inverse for this is going to be in quadrants 1 and 4, just like our sine graph. So for this, we're doing the tangent inverse of y is equal to x. So if I graph this, if I have negative pi over 4, negative 1, I'm going to have negative 1 pi over 4 on my graph. So my graph would look something like that, and then I have to have my asymptotes going this way, so it turns your graph sideways. So that would be my inverse graph. It's called the inverse tangent or arctangent. And we can again use the inverse notation, or you can use arctangent. So we have properties for the inverse tangent as well that we need to know, which are right here. And so let's just do a couple examples of this. So remember, anytime you have arctangent or tangent inverse in your equation, you can only, just like sine, be in quadrants 1 and quadrant 4 for your answers here. So I want the arctangent equal to 1, which means I'm doing the tangent inverse of 1. So I'm trying to think the tangent of what angle gives me a value of 1 on my unit circle. So if we think about this, where do I get 1 on my unit circle for the tangent? at a value of pi over 4. So this is equal to an angle of pi over 4, which is right here, because remember it's sine over cosine, and then that value have root 2 over 2 divided by root 2 over 2. For B, that is not something that is on my unit circle, so I can use my calculator to evaluate it. When I do my calculator inverse tangent, I get 1.5634. Remember to make sure you're in radians. Now for these last two examples that we're going to do, actually last three, notice that you have the tangent arc cosine of 2/3. Now this one's a little bit trickier. It's not like having the properties where you have both tangents in your equation. Anytime you have two values that are different, you're going to have to do something different to evaluate this. So this says we have the tangent, and then we have the cosine inverse of 2/3. Now for this, the cosine inverse of 2/3 is not something on my unit circle. So if I want to evaluate this, I am going to do that by making a triangle. So that's what I'm going to do first. So on my graph here, if I look at this, the cosine of 2/3, remember cosine inverse means we're in quadrants 1 and quadrants 2. So quadrant 1 and 2. So 2/3 is a positive value, so I know I'm going to be in quadrant 1 because of that. So for this, I get my triangle. Cosine is adjacent over hypotenuse. So this is what I have so far. So remember, when we're finding the cosine inverse of something, we're actually finding the angle. So if I write this out, I'm saying the cosine of what angle gives me 2/3. So we're calling this our angle. So if I do that, then the cosine inverse of 2/3, I'm going to say let that be equal to x. And all I did was switch my x and my y. So that's what I'm doing up here. So really, if the cosine of 2/3 is equal to x, well, aren't I trying to find the tangent of x? I'm just trying to find the tangent of that angle. So in order to evaluate when you have two different trig functions in your equation, most of the time you're going to have to, if it's not something on your unit circle, you're going to have to make a triangle and then use that angle, because the angle doesn't change just because you're doing different trig functions. What does change is the answers that we get out from it. So now the tangent, remember, is opposite over adjacent. So that means I need to figure out what that third length is. How do I do that? I use the Pythagorean theorem. So I know if I call this side A is equal to the square root of 3 squared minus 2 squared, which gives me the square root of 5. Now I can figure out that the tangent of that angle of x, which is the same thing as this right here, you're finding the angle for that, is equal to root 5 over 2. So this would be my solution to the entire equation. So this is equal to root 5 over 2. And again, it's because the angle doesn't change. You're just changing instead of the trig function that you're using. So if I look at B here, notice that I have the cosine sine inverse of -3/5. -3/5 is not on my unit circle. So again, I am going to draw a triangle. So for this, I'm saying the sine of, I'm going to call it in this time instead theta. So the sine of theta is equal to -3/5. So we're doing the sine inverse of -3/5, which is equal to some angle. So if I want to find the cosine of that, I'm really doing the cosine of theta. So -3/5, remember that sine we know is in quadrant 1 or quadrant 4. So if it's negative, we have to be in quadrant 4. So I'm going to draw my triangle going down this way, and this is going to be theta. I know that we have sine, which is opposite, so this has to be -3 over 5 because our hypotenuse is always positive. And now I need to figure out what that other length is, which is a 3, 4, 5 triangle, so it's going to be +4 because the cosine is positive in that side. So if I want the cosine of the angle of theta, it's equal to a value of adjacent 4 over hypotenuse 5. So this is all equal to 4/5. And again, when you don't have something on your unit circle, you need to draw a triangle in order to help you figure out what that other angle is, because you're using the same angle for each of them. So the very last part, we'll do example 6 in class together and look at that. But the very last part, now we have our table here. So this is kind of a nice table just to kind of put everything together. So we have our inverse functions, and remember there's two different ways that you can write them. So I wrote down the domain and range, and I also wrote down the quadrant that we are in for each of them. The last part we have, which we'll talk about in class as well, are the secant, cosecant, and cotangent. We don't usually use those as often, but we will also take a look at how to get those values, and also notice that the quadrants are given over here. So it's really helpful to notice that sine is in quadrants 1 and 4, your tangent is in 1 and 4, and also cosecant, which is your sine reciprocal, is in quadrants 1 and 4. And notice that cosine and cotangent and also secant are in quadrants 1 and 2 for your answers when you're using the inverse trig functions. So we will do a lot of practice of this in class, but make sure you bring it with you, and we'll go over example 6 together as well.